Hello, everyone. I'm Saeed Jafari. I'm a linguist working on animal vocal communication and language evolution. My studies are actually based on linguistics and cognitive science, and I'm focusing on how language shapes the way we think in human languages. And recently I started working on complexity underlying vocal communication and cognition across species, especially on birds, humpback whales, and bottlenose dolphins. In this talk, I'm going to talk about how we can assess technosignature signals through cross-species vocal communication, part of the theories and hypotheses and evidence presented on the dolphins, whales, where the research gets Doyle, McQuan, and Sharp studied during the last 2 decades. Actually, they created a whale SETI team. It's a cooperation between SETI Institute and University of St. Davis. And this has really helped me to actually do this research and overview based on the comparative analysis. Be sure this planet with over 7,000 human languages. And I want to stress something that at the start, each one is its own cognitive universe, its own way of carving up reality. Historically, we have treated language as a last bastion of human uniqueness, like a binary wall, us on one side, everything else on other. That mindset fits on anthropocentric or anthropodenial, where we risk missing sophisticated intelligence simply because it doesn't fit our Indo-European template. So what is really important is this. If we ever hope to recognize the technosignature from the stars, we first have to master complexity of vocal communication right here on the planet by focusing on the bioacoustic structure of our co-inhabitant. We shift from the subjective hunt for meaning to the objective quantification of the information complexity. And we are beginning to see a continuity of complexity across species. So the stage for intelligence has to look beyond ourselves to universal rules of communication. Let me start one of my favorite animal that I'm interested in to work on actually the vocal communication. It's a songs of humpback whale. These songs aren't random at all. They are organized in the nested hierarchy, discrete unit combined into phrases, and phrases repeat into themes, and themes sequence into the full song cycle. The structure is rich enough that you basically need network modeling to map its a small word connectivity. Actually, what we reviewed that based on humpback whale songs, we recognize a couple of the layers on their actually communication systems, that it is really related to the cultural learning actually of this animal. Now, unlike humans, where we often prioritize semantics, humpback show rigid cultural conformity across ocean basins, and they undergo annual revolutions where song patterns are rapidly replaced. They don't have any specific lexical syntax of human speech, but their signals follows this law of last effort, as you know, balances unification and diversification, and that statical coherence lets us estimate potential communication capacity even when we haven't decoded a single word. The next one is a dolphin. Dolphin give us different angle. This is a bottlenose dolphin, are highly social and tool using, and they rely on the acoustic vessels to negotiate group life. One of my favorite finding is that the baby dolphins are born bathing. They explore the acoustic space a lot like human infants. Over development, their repertoire converges on the Zipf distribution, which is a crucial sign of moving from the random noise toward the structure, rule-bound communication. They have also used signature whistles, learn vocal labels that function like names. So they can address a specific individual in this fission fusion society. And the last, animal that I actually worked for my dissertation, it was, on the songbirds. The Persian teeth and the Japanese teeth has provided the first experimental proof of the commerce. Commerce is something that actually connects the word to the verb to the subject. And this is something that we found in a couple of species in the jungle in the fieldwork. Commerce is a wide cognitive capacity once treated as a unique basic property of the human language. The common meaning bearing calls like an ABC scan call and the requirement call into the sequence where the overall meaning is compositional. Receivers treat this combination as a single unit, but only if they organize from a single source. So they're not just reacting to the close timing, they're recognizing a structural syntax. And the monkey, like Campbell's or putinose species, can combine item with a two-slit mold. But those systems lack the recursive power of the true syntax. Recursion in the language is something looks like that. You can reference something to the past and make a couple of the sentence something like present, future, and the past. The Persian text goes further. Use the specific ordering rules to decode novel sequence given a who did what structure. This tells us the evolutionary Rubicon of syntax is graded overlap, not a struct divide. And the next part is this is directly to the my talk is about language evolution. What language evolution looks like if we stop arguing about the difference in kind and adopt prototype theory. In this view, language is a cluster of features, generativity, recursion, and displacement. And different species system can be more or less typically related to the central prototype. So you don't ask language or not. You ask how close the prototype and in what dimensions. The integration hypothesis then says human language arose rapidly when two pre-adopted systems merge an expression system for structural patterns seen in bird songs and the lexical system for real-world reference found in the primate alarm calls. Bird sings with a syntax but without meaning, primate call with a meaning but without syntax. Human are uniquely mainly in how fast and how completely these two layers integrated while the operation merge. And the matter for SETI, because this is evolutionary expectation, it gives us a template. Look for a signal that similarly integrates the structural process referential capacity when we evaluate candidate technosignatures. As you all know, timing matters if we are going to calibrate what fully developed language even means in the first place. Comparative studies of the early human population divergence suggest that our linguistic capacity was already full present about 135,000 years ago. One of our friend Shigeru Miyagawa's genomic analysis shows that because of all descendants population from the first system population divergence process full-fledged language, the cognitive faculty must have predated the split. This is the saltational view. The core components were assembled suddenly, not through endless gradual tinkering, and the piece doing that heavily lifting here is merge. This is putative gradual development that let humans organize and systemize modern behavior and transmit knowledge at this scale. So I bring this up in this talk about the technosignature because if we can calibrate our own evolutionary timeline, we can estimate the complexity to brain science ratio and use conversation pattern to infer development state in the potentiality civilization. We're not looking for the Martian nouns. We're looking for the universal signature of the recursive set formation. Finally, let's talk about the methods. Because what is really important is we do is rigorously and do it systematically, not by intuition. We need network analysis to identify underlying syntactic features in mammalian displays. In humpback whale signs, for example, direct network modeling reveals a small word structure. Highly connected hubs give you a stability even while the surface pattern voices. The stability is maintained by deterministic motifs, where the specific units are always followed by the predictable others, keeping display a stereotype and parallel to the human language and the music aren't just cued, they are diagnostic. They suggest, a colleague from the University of St. Andreas, they suggest actually syntactic rules are taxon general, popping out whenever a species has to learn and transmit complex information efficiently. So, as I said earlier, the payoff is practical. Network analysis lets us back out these rules from Technosignature without needing to translate semantics first. By mapping connectivity, we can distinguish astrophysical noise, pulsar are a classic case, from a structural, non-random conditional probability that define intelligence communication across the cosmos. To move beyond the anthropocentrism, we apply a shared quantitative framework across the species, same question, different vocal system. So we analyze acoustic units, sequencing rules, and transition network structure in a comparable way. The first step is a unit discovery, tailored to the subject, calls in primates, syllables in songbirds, phrases in cetaceans. And when the data are continuous, like the humpback oceanic displays, we use the time frequency segmentation to eliminate discrete elements before we do anything else. Now, why I'm emphasizing this? Because this primarily analysis gives us a rigorous empirical contrast to the universal grammar I would say, universal grammar perspective. By examining the core principle of the simplicity, universality, and the operation merge, this is part of the syntactic part of our language. There's somehow, visible on the animal communication. We can ask now whether cross-taxon structural similarities behave like candidate universal, or whether semantic remains strictly locally grounded. This is a pivot from the bioacoustic to, linguistics, science of the alien languages or extraterrestrial languages. We can identify systematic information bearing patterns that transcend biological lineage. Then we have a robust way to evaluate technosignatures, and if we don't discard a structured complexity just because this is local semantics are unfamiliar. That's why we need to intentional signals. Primary diagnostic is a Zipf's law, where we analyze the rank frequency distribution of signals to dictate language likeness. We plot the frequency of the unique occurrence against its rank. Human language and animal system like dolphins, whistles often converge on a slope near a -1. That gives you a quantitative shape that looks like language. But Zipf is only the start. We have to separate possibility of occurrence and unconditional frequency of a unit, like a phoneme, very smallest part of a word, or word regardless of context. From the conditional probability, using notion like P of U given Q, we ask, given the previous unit Q, how predictable is the next unit U? That's a sequential dependencies of what let you reconstruct missing piece. In human, conditional dependency remains meaningful up to roughly the 9th order, which gives a clear limit on the long-range dependency, and that enables contextual recovery or close-like inference. You can fill in the blanks in a cropped text. There are more units, ambiguity rises, but the sequencing rules will provide a mathematical scaffold for information recovery in noise. In noise, a noisy environment. This leads directly to next entropy. The next part is about intelligence content. To quantify the intelligence content of a signal, we use Shannon entropy to measure unit level uncertainty. Conditional entropy then measure how much that uncertainty is reduced when the preceding constant is non-null. From here, we calculate the entropy rate or average uncertainty per simple in a sequence. Here, in contrast, a matter for SETI, astrophysical source like the Vela pulsar can show high entropy with almost no change across orders. Knowing what comes before doesn't help. Dependency, because longer context carries real predictive power. Notably, human word entropy typically persists up to about 9 order 9, I think. If longer context keeps improving prediction, that's a strong intelligence cue. So, in practical terms, any interstellar messages with this kind of language like a structure is tactically built for a receiver whose internal biology support comparable computational machinery for processing nested hierarchy. That sequential probabilistic structure becomes an intelligence filter, separating legitimate technosignature from the periodic astrophysical, noisemakers. And by mapping those dependency, we can place a candidate ETI signal on, an evolutionary line of communication complexity as a, quantitative proxy for transmitted social or cognitive complexity. So let me stress one more implication of the rule structure in bioacoustic displays. It supports the filling in the blanks. You can model the ocean acoustic channel as a communication channel, basically like a cell phone line with a static or distortion. Analysis of Alaskan humpback whales shows that they employ noise adaptive vocal production when confronted with a bottlenose. Much like humans speaking more slowly in a loud room, the whales reduce their rate of vocalization. But if we observe significant theoretical versus observe, a slowdown gap, information theory suggests that should have slowed down much more to maintain a clear channel. Instead, they slowed down by approximately the fifth of, recorded amount. So, what does that mean? It indicates, their system has enough internal redundancy and rule-bound structure to recover the remaining 2/5 of the signals, so they can communicate efficiently even under the serious degradation conditions in that noisy environment. This is something that, from real research, I think this is something that a group of veterans at the SETI Institute, have been done about, 7 years ago. And, in our quest to build a communication intelligence filter, we operate under a practical assumption. Bioacoustic sequences have a sonic equivalent of words, discrete functional unit that act as building blocks of complex messages. If we can characterize the statistical distribution of these units, we can rank intelligence content without needing a Rosetta Stone. Let me give you a concrete contrast. Some packways provide a tired laboratory. Their songs primarily used on mating routes like those in Hawaii shows rigid hierarchical repetition. Units into phrases into themes, themes into cycles, but their social calls and feeding calls during the coordinated Babel nets feeding have distinct non-sung structure with their own patterns. Dolphins sit somewhere else again with a core repertoire of approximately 50 signals types, while the humpbacks can utilize hundreds. Thus, the difference changes the combinatorial space. We are now extending this approach to the span verbs out of actual debates, aiming to high order entropy estimation to estimate the upper limit of the non-human communication complexity. This brings us back to local semantics. Meaning may remain locally grounded and elusive, but information-theoretic structures defines the system is carrying capacity. The primary challenge remain accurate unit classification across very different sensory and environment contents. A critical objective in SETI is discriminating astrophysical source from the genuine technosignature. And I want to emphasize, we do not do that by vibe. We do it by ranking candidate through the communication intelligence filter. Historically, the discovery of the pulsar is, a cautionary tale. They were dubbed Little Green Men because their extreme regularity looked for a moment like an intentional beacon. But information theory, diagnostics strip away from the mystery. Develop a pulsar, for instance, produce a Zipf slope of approximately minus 0.3, and it shows a total lack of the conditional probabilistic structure. That combination is incompletable with any non-language system fits the profile of a natural astrophysical source. And at the Allen telescope array, 42 telescope observing in the 1 to 10 gigahertz band, a group of the researchers are now moving to beyond simple narrowband radio carrier searches. They integrate Zipfian analysis and higher order entropy structure as a complementary layer to identify Zipf consistent candidate phrase. If a signal clears that necessary statistical bar, it motivates a deeper search for syntax-like structure, so they can quantify the messages through complexity level rather than guessing. And for the last part, I would like to actually talk about main factors of the first contact message, the framework that we can access. In designing or detecting the first contact message, we have to navigate the tension between the universal grammar and local semantics. The universal grammar side assume a recursive core, something like merge and recursion in the human language and in animal vocalization, which may be a computational necessity for any intelligence evolving in our universe. But the local semantics demands us that meaning is constrained by the medium, the biology of the sender, and that's the practical design constraint. So the message robustness becomes permanent. We may need a varied media from electromagnetic light to acoustic channels or even physical objects. So the signal stands out from the cosmic static and carries recognizable mathematical patterns for easy recognition. And here's a punchline. Mutual intelligibility is a dual task problem. We have to ask what the ETs mean while also structuralizing our own signal to help them infer our intent. Success depends on identifying structural logic and transcend specific semantic boundaries. And this is something that we have to take care about, the relation between the animal vocal communication and more than 7,000 languages in all the world, the different part of the, our planet, because this is something we have to practice in our own planet, because there's a lots of sort of the communication that we have to think about. And then we can actually search for extraterrestrial intelligence and, assess their, signature and signs, among these guys. Thank you so much.
Sorry, Martin, you're muted at the moment.
Yes, now you're fine.
Yeah, I have to press yet another button. So thanks to Saeed again. And so we now have a bunch of questions. The first few being directed at Hilding. And that's one from Joseph Lazio, who points out, I suspect that the boundaries that you showed on the maps of North America have not been static over the last 10,000 years or so. Why are the current structures more important than those from, say, 5,000 years ago?
The map I showed is from nativelands.ca, which is an important resource for looking where most First Nations claim territories today. Of course, those, they're not even really boundaries because peoples overlapped, they moved around. It is just a reflection of First Nations and Inuit and Métis territories today.
Okay, further question to Hilding from Caleb Strom. What do you think would be a specific example of a nature-enhancing technosignature? Possibly evidence of planets that appear to still be habitable even though they are beyond their natural habitable zone?
Yeah, that's a really hard question. So to just take your example of habitable, when we define habitable, we're just saying something relative to us. The view of being habitable could be different for something else. So being more biological or super biological is a little difficult to tell what that means in general terms. So I have a very challenging view to actually say this in specific examples, because in the end, we do tend to reduce it towards our own experiences.
Okay. Further question. Isn't view of the indigenous rather reductive and operating under the assumption that the indigenous is a single static philosophy rather than a complex range of cultures that change on fairly rapid timescales?
As I noted when I talked about these axioms, these are in the modern discourse through indigenous methodologies, indigenous studies. Indigenous is reductive because it is not defined by the peoples who are called indigenous. It's defined largely by the society around them. As noted, there are Mi'kmaq knowledges, Seneca knowledges, Haudenosaunee knowledges, and so on. So I don't think it's necessarily reductive. I think there's just lots of things we have in common. And it is a static snapshot in the same way Western science is a static snapshot.
Okay, now there comes a question that Eric Kopeler considers not being really answerable, is whether a biosignature can be larger than a planetary scale. I suppose we would have to consider the possibility if a solar system scale structure were discovered. Anyone wants to have a go at that? Perhaps Milton?
Hey, I would know. I think we cannot. I'm suggesting that animals and other organisms are doing things that we perhaps are not taking a serious look at. So perhaps in other biospheres, you could find living organisms trying to go up into space and building structures out in space. I don't know if that's possible. That sounds quite far-fetched, but why not?
Mm-hmm. So a question to Milton from Caleb Strom. In your view, what is the difference between a technosignature and a biosignature? Would it be one of kind or degree?
That's an interesting question, and it's another comment on the chat as well, because if you define technosignature like needing intelligence of a form that produces concepts and applies concepts, and it's complicated. Of course, beavers are not doing that. They're doing something from that. That's why I stated in my presentation, they're doing this from innate behavior. It's been selected, naturally selected for generations and generations. So it's not a question, there's no question of individuality perhaps there is. I mean, different beavers can do slightly different dams, but it's so different. I would say it's categorically distinct. But in biology, we're quite used to this kind of situations where we, as humans, psychologically tend to put things in different boxes, and they're actually continuous. So my view is that there's probably lots and lots of stuff between a proper biosignature or a simple biosignature and a simple technosignature.
It reminds me of discussions that we had in St. Andrews with the Global Research Center for Diverse Intelligences. And you know, at that point, you realize intelligence also can be seen as a spectrum, rather than something that just fits directly into a specific category and is restricted to humans.
Yeah.
Now I have a series of questions for Saeed. The first one from Diana Solano Oropesa. Why do the different data diverge so much from Zipf's law at high and low ranks?
Can you hear me, or are muted now? Yeah, I'm not on mute. So Zipf is a kind of a middle of the curve, right? You know, it fits best where you have enough data and you know, nothing weird is dominating. At the top ranks, the super common stuff, I think, like the and of in English, or really stereotypical types in animal data gets used for lots of boring but necessary jobs. So these units become too frequent, and they pop off the clean Zipf line. And at the low rank, you are in the messy tail. You know, you just don't have enough sample, tons of item appear only once or twice. And honestly, segmentation unit discovery can invent a new unit. In new units by accidents. Finite data makes the you know, tail jittery, I believe. You know, Zipf looks like you know, something that we can disseminate. You know, we can distribute all of our data, like phoneme, like, you know, letter in English, in the Chinese, in different language, and see that. Is there any language based on, you know, most common words and different, you know, verbs, adjectives, and, you know, a subject in a single language?
Okay. Brian McConnell points out that it is important to distinguish between the carrier, which may be narrowband and easy to detect, and the information it transmits, which may be rich in structure and information content. So how does that relate to what you said in your presentation? So Saeed, you showed these, you know, signals and then the language information. Does that has any?
Sorry, Martin, which question? My connection is not stable. Sorry, can you repeat it?
I repeat. So Brian McConnell pointed out that it's important to make a distinction between the carrier, which might be narrowband and easy to detect, and the information it transmits, which may be rich in structure and information content. So is this in line with what you said, or does that change anything to what you stated?
No, this is something that I said. Of course, you know, this sort of the transmit. Now we are, you know, working on the, you know, vocal communication here, you know, through the animal species. But, you know, something from the, you know, astrophysical data or something that we carried. It is, you know, something that a group of my friends who are astrophysicists, because I'm a linguist, it's a little bit hard to answer this question because it's part of the, you know, mathematical process that our friends have been done.
Okay, question from Eric Coppola to Saeed as well. Would Zipf's law still apply to technological data transmission? For example, an analysis of internet traffic. Has such a study been done? Much internet traffic is encrypted and compressed, both of which remove redundancy. Wouldn't it appear more noise-like, or does it still preserve some of Zipf-like relationship in, for example, length of the communication rather than content?
Yeah. So it can, but it really depends on what level you are measuring. If you literally take payload bytes from the HTTPS, then encryption makes it look noise-like by design. And if it is also compressed, that strips out of a lot of redundancy you would normally exploit for the Zipf's entropy structure. So at the symbol level, you should not accept a clean Zipf curve. Something that we have to we are trying to approximate randomness.
Okay, there's a question from Milton from Benjamin Fields. How do we know the beaver dam is not technology? Short of reading a beaver's mind, can we ever know they're not intentional in their behavior? And by the same logic, if the dam was made by an unconscious but functional robot, is it not a technosignature because there's no intentionality behind it?
Yeah, funny question. I would guess, as I said, it's innate behavior. So if a beaver is not taught by its parents how to build a dam, it will probably know how to build a dam nevertheless. But for us humans, the things we usually build depend on cultural evolution. So I guess that's one difference at least. So beaver dams come from natural selection, and human dams come from cultural selection, from acquiring knowledge because of our brains only in a conscious way, let's say. But I agree, it's a kind of murky terrain, right?